morning, everyone, and today we're going to be covering one of the most important topics for AP Physics exams, rotational motion.
That's right, John. Rotational motion is all about objects that rotate around a central point. We'll cover the basics, including rotational kinematics, dynamics, and energy.
All right, let's go ahead and start with some key concepts. First, angular displacement, which is the angle through which an object rotates. We already know that angular displacement is measured in radians, but it's important to always remember this. 2 pi radians is equal to 1 revolution.
Good point, John. It's important to remember that there is a correlation between linear equations and rotational equations. We can practically use the same ones for both. Here are the key differences. In linear equations, we use x, and we use v, and we use a. But in rotational equations, as substitutes, we'll use theta, we'll use omega, and we'll use alpha.
All right, so let's go ahead and get right into it. We already know that angular displacement is shown by theta. Next is angular velocity, which is represented by omega. It's the rate at which an object rotates and is measured in radians per second.
The formula is omega equals the change in theta over the change in time. And just like in linear acceleration, we just use omega instead of theta to find acceleration. So for here, alpha would be equal to the change in omega over the change in time.
Now we're going to talk about some of the equations of rotational motion, which are quite similar to the linear motion equations, but adapted for rotation.
As you can see here, the equations are just the same, except instead of x, we use theta. Instead of velocity, we'll use omega, and instead of acceleration, a, we'll use alpha.
Great. Next important topic is torque, which is the rotational equivalent to force. Torque, signified by tau, is calculated by torque equals R, which is the lever arm, times F sine theta, where F is the torque applied and theta is the angle between time and the lever arm.
Exactly. And torque causes angular acceleration according to Newton's second law for rotation. This law is tau equals I A, where I is the moment of inertia, which is a measure of how much resistance an object has to rotational acceleration.
Speaking of moment of inertia, it's crucial that we all understand that it depends on the mass distributed relative to the axis of rotation. For example, for a solid sphere, the moment of inertia is equal to 2/5 mr squared.
And for a solid cylinder, it would be I equals 1/2 mr squared.
And let's not forget about rotational kinetic energy, which is given by K equals 1/2 the moment of inertia times omega.
Exactly, John. And angular momentum, L equals IW, is conserved in a closed system unless acted upon by an external torque.
That's absolutely right, Jason. Now we're going to move on to a practice problem to make sure you really understand what we're teaching.
So what we're going to do here is the equation. We're going to use the equations from what we just learned. The object is rotating about a fixed axis such that its rotational inertia about the fixed axis is 10 kilogram meters squared. The object has an angular velocity, omega, as a function of time, and that equation is given right here. Alpha time cubed minus omega 0, which is the initial omega, where A is equal to 2 and initial omega is 4. The angular displacement of the object from t equals 1 to t equals 3 is what we're trying to find. So for this equation, what we're going to do is we're going to integrate the equation they gave us here, plugging in all the values that they've given us from 1 to 3. So in this equation, theta equals the integral from t equals 1 to t equals 3 of this equation, substituting 2 for alpha and 4 for omega initially. So that would be 2t cubed minus 4. dt, of course. This is equal to 2t to the 4th over 4 minus 4t. Minus 4t from 1 to 3. Solving for that gives us 32 radians, which is the answer we're
With that, we found the answer to our problem, and now we believe you guys are ready to kill rotational motion on the AP Physics exam. Good luck.
Fine.